Okay, we're starting. So hopefully this wasn't so bad. It was short at least. We'll see. Last time we stopped with exponential models. So we're going to continue talking about those. I think I told you last time how to recognize when to use one, when there's a useful, and some applications of them, right? I think that's what we covered. I didn't actually tell you what the functions look like, so we're going to continue with that definition. Basic exponential function has the form y equals c times a to the x for c not 0. So that's the form that it looks like. But that's just the basic form. Transformations of this tend to be exponential also. Right, so for example, if I have something like 3 times 2 to the x and then I add a 1, it's still an exponential. It's just shifted up, right? So remember we talked about transformations, how we can add things, subtract things, multiply by constants, reflecting the x-axis and y-axis and all that. You can do all those to the exponential and you still get another exponential, but this is the basic form. Important to note here, c and a are constants. Right? So this has to be a number. So examples of exponential functions are like y equals 2 to the x, y equals 7 times 3 to the x, y equals 4 to the x plus 1. Something like y equals 3 to the minus x. Right? Now that one you might be worried that it doesn't actually fit the form because it says a minus x instead of x, but don't worry because you can think of this as 3 to the minus 1 to the x. So it's like your constant is actually 1/3. Right? That's the same as 1/3 to the x. Right? So you could do a reflection and you still get an exponential because you'll be able to write the base as just an inverted number. Right? So this is a basic exponential function. A constant times a constant raised to a power. So it's very important that you remember that these two are constants. The variable is in the power. That's what makes it an exponential. In the flip side, vice versa, if the x is down here and there's a number up here, it's going to be a polynomial or something else, right? Like an x to a power. It doesn't behave like this guy. So some non-examples. Right? So like y equals x squared is not an exponential, right? Now these two might look similar to you at first because they both have a 2 and they both have an x and they both have a power and a base. But the fact that the base is a constant and the power is a variable, and here the base is a variable and the power is a constant makes all the difference in the world. The graph of x squared looks like this, while the graph of 2 to the x, which I'm going to talk about graphs later, they look like that. They look very different, and they behave very different. That guy 2 to the x will increase a lot faster than x squared, and I do mean a lot faster. So that's what an exponential function looks like. Right now, let's look at the graphs. The graph of the typical exponential function. So if I wanted to graph y equals a to the x, here I will assume that my a is greater than 1. If my a is not greater than 1, it's okay because I can write it as an inverse and then just use the reflection rule. Right? So if your a is a constant greater than 1, so like 2 to the x or 3 to the x or something like that, the graph will look like this. It pass through 1. And on this side, it will continue to approach 0. It will continue to approach the x-axis, but it will never actually reach there. And on this side, it starts to increase very rapidly. In fact, at some point, it will increase faster than any polynomial you can think of, no matter which polynomial you take, right? So your polynomial might beat it locally, but it will always win in the end. The exponential is always going to be bigger than any other polynomial, right? So even if I say x to the 1,000th power and versus 2 to the x, right? Or even 1.5 to the x. Eventually, 1.5 to the x is going to be a lot bigger than x to the 1,000th power, or x to the millionth power, or x to the billionth power. X to the billionth power might be bigger than this guy for a while, but eventually this guy's going to overtake them. Exponential functions grow really, really fast. Right? They might start out slow, but eventually once they get going, they really pick up. That's one of the basic properties you want to think of as the exponential function. They grow really, really fast. And that's what the graph looks like. Right? So this is where we have a constant a to the x. So examples like y equals 2 to the x, y equals 3 to the x, y equals 17 to the x. All those graphs, they will behave like this, but the bigger the base, the steeper it will rise. Right? But this is the basic form of the exponential graph. And of course, we can do transformations. Like I can talk about y equals a to the minus x. And what would that look like? A to the minus x. If I replace x with negative x, what happens to the graph? Reflect where? Over the y-axis. So I'm going to reflect it like this, and it would look like that. Right? So this is also, by the way, it's pretty much the same as another graph, y equals e to the x, where e is less than 1 would also look like this, right? Because you can write that as 1 over a number bigger than 1 and then take the negative power. So graphs will look like that if you have a negative power. Right? It's useful to know the other reflections as well. So if I have y equals minus a to the x, or y equals minus a to minus x, what would this one look like? Huh? Minus a to the x. What picture is that going to look like?
Reflected over the x.
Reflect what over the x? Reflect what over the x? Reflect this over the x?
Yeah.
Reflect that one over the x, right? So here I have a to the positive x, so it's kind of like this guy, but I put a minus in front, so that one is reflected over the x-axis, and that would look like this. Into negative. This guy is reflecting that one over the x-axis, so that one will look like that. So just knowing what the graphs look like will come in handy later on when we're comparing functions. Things like in limits and curve sketching, this is going to be important. Just knowing how functions behave can tell you a lot about them. Where you can get away with solving problems without doing any computations because you kind of know how the picture behaves. So this is like the standard a to the x graph, and this is kind of in your mind what you want to picture when you think of an exponential function. What else do I want to talk about? I'm going to remind you about the laws of exponents. It'll come in handy here. In case you want to operate on exponential functions. So things like the first law we can talk about was on a quiz, I think. If I multiply two things that have the same base, different powers, what do we get? You add the powers. You multiply things of the same base, you will add the powers. Okay. 2. What if I divide things of the same base? Subtract the powers. What if I add a to a negative power? How do I think of that?
1/8.
Correct, the reciprocal. 1/8 is. What if I add a to one power and I raise that whole thing to another power? You multiply the powers. Another one. What if I have a base and I have a fraction in the power? Huh?
It's a radical. That is the radical sign.
There's a radical, a, and what does the m and the n do?
M is the outside.
M is the exponent, n is the outside. Now if your a is positive, it actually doesn't matter which one you do first. So they're the same if a is positive. You can actually raise it to the power first and then take the radical, or you can take the radical and then raise it to a power. And usually you'll want to do the one that's more convenient for you. Usually taking the radical first would be convenient. So example, if I look at something like 9 to the 3/2, right? You have a couple options for that. You can think of this as radical 9 and then cube it, or you can think of as 9 cubed and then take the radical. Now one is going to be easier than the other, right? This one should be easier, right? Because then 9 cubed times 9, who remembers 9 cubed off the top of their head, right? And then that's going to be a big number, probably 729 or something like that. And then you have to take the square root of that, and it's going to get annoying. As opposed to here, if I take the square root of 9, that's easy. I know that that's 3 right away. And then I'm going to cube that. So I know the answer is going to be 27. So this one's easier to work out, that one's harder. And I can choose which one I'm going to do in general. Right? The reason being is that the reason I can choose is because of this one. It's because of the multiplication of powers. So the things I can think of as m over n, I can think of that as a to the m and times 1 over n, it's going to multiply. Or it can be a to the 1 over n and then times the m. In either case, I'm multiplying these two numbers, it's going to give me the same thing. Why I care about the a is greater than 0 is because if my n is even, remember the domain will mess up. But in general, you can do it either way. If your n is odd or your a is positive, then it doesn't matter which one you do first. The mnemonic for this one, which I like to remember, is called flower power. The a to the m over n. What you do is this power, kind of think of it as flower. That's flowers, right? Notice that this is like your division sign. The bottom is the root, right? Like the radical. It tells you that the bottom number is the root. The top is the flower, which rhymes with power. It's named flower power. So you know that if you see something with a fraction in the power, the top is the power, the bottom is the root. And so that's how you get that formula. A common thing that you're going to see all the time is something like x to the 1/2, right? Which is, according to this rule, what's that? Just the square root of x, right? You can use these interchangeably. Right? So later on, I'm going to be giving you some rules. When we get to derivatives, that's chapter 3. I think it's in 3 where I give you the shortcuts. where the rules are going to help you with power. So if I throw something at you with a radical, what you're going to want to do is you're going to want to convert it to a power in order to apply the rule. So this guy's going to come in handy later on, as well as in this section. So it's very important that you remember flower power. You can switch from radicals to powers at will, and it shouldn't be a big deal. What else do I want to tell you? Well, a couple of other rules I can remind you of. Division and multiplications. How many rules did I say already? 5? Is it 5? So rule 6. I have two things multiplying and I raise that to a power. What happens? Powers distribute across products. They don't distribute across sums. If there's a plus or minus here, it's not going to work. But if there's a multiplication, I can actually take a power and attach it to each part. Similarly for division, powers distribute across divisions. So if I have a fraction raised to a power, I can raise the numerator to that power, divided by the denominator raised to that power, and it'll still work. That's just reminding you guys of the rules. I think a lot of you remember those already. Let's start over here. We're going to talk about a very important exponential function. It's a very important exponential function. The function e to the x. Has anyone seen that before? Okay. Brings back good memories, doesn't it? Good times. It's a very important exponential function. Y equals e to the x. It also looks like this guy. Because e is actually a constant. Right? That's important to know. Right? So e, it's a letter, but it's actually a constant, right? What makes this a variable function, what makes it an exponential, is the power that I can put on the e, right? But e itself is a number, it's a constant. It's actually 2.71828, and it kind of repeats. It's an irrational number. It's a very, very important number, right? But it's a symbol that means a number. So anytime in this class when I write the letter e, it actually means a number. It's kind of like pi, right? So if you see pi, you know it actually means 3.14159, all that stuff. So it's a letter that we write that means a number. E is exactly the same thing. It means this number. It actually equals to the limit as n goes to infinity, 1 plus 1 over n to n. Don't worry about if you don't know what that means yet. We will know what that means in chapter 3. Or chapter 2. I think we do limits in chapter 2. So e is the value of this limit. It's that number. You wonder why we call it e. It's because it was discovered by a mathematician by the name Euler. He's a Swiss mathematician, very prolific his entire life, which is actually pretty rare. Most mathematicians make their major contribution by their late teens or early 20s, and they never do anything worth note for the rest of their life. So math is a young man's game. So all the things you study in your math textbooks where you're like dying, it's like kids came up with it, like little kids. Euler actually, though, he was like producing math results like all into his late, he was going blind and all sorts of stuff, and he was still just cranking out math. It was really exceptional. There are tons of things that are named after this guy. There are all sorts of things named Euler, and eventually they just gave up naming things Euler because it's confusing everybody, and they started naming it like E. which stands for Euler. But yeah, he's all over the place. You cannot read a math book where something in that book wasn't somehow related to this guy back in the day. Okay? So E comes from Euler, but you don't need to know that. It is a constant. And the function, when I make that into an exponential, y equals e to the x, it is a very important function. This is the nicest, sounds subjective, but it's actually, it makes sense, function. It's the nicest exponential function to do calculus with. So it has a lot of nice properties, like its slope at x equals 0 is 1, which is very nice. So if you look like y equals e to the x, and you're talking about the slope at this point, the slope of that tangent line, we'll talk about that more, is actually going to be 1. And its slope at any point is equal to its y value. And it's the only exponential function that does this. Another thing that's nice about it, it's own derivative. Derivatives we'll talk about in chapter 2, so you'll understand what I'm talking about there. Derivative, we will discover, is just a fancy name for the word slope again. So basically at any point on this function, if I take here and I find out the slope at that point, like draw a tangent line, the slope of that straight line is actually going to be exactly equal to the y value at that point. Right? And 0 is the only other function that does that. So that's a really special property. Y equals 0 is the only other function for which that is true. Right? And 0 isn't a particularly interesting function. It does nothing. Right? So this is the only non-trivial function where the slope is actually equal to the y value at any point along the curve. So there are a lot of times when we have other exponential functions, and when we want to do calculus, we're going to actually rewrite them as the e with the base e. And there are a lot of things when I get to logarithms we're going to talk about with base e. Because E is very nice for calculus, because a lot of things just work out really nice where we don't have to do a lot of work to get to an answer. Because a lot of times the answer is just going to be itself. And that's pretty nice to work with. So it's a very nice function. It's own primitive as well. That's when we get to antiderivatives. That's way at the last chapter of the book, so we're not going to talk about that for a while. But that's another thing, right? So if I take a derivative, it's going to be the same. If I take an antiderivative or an integral, it's going to give me the same function plus a constant, and not a lot of functions do that. So there are a lot of nice things about E. It is the exponential that describes continuous compounding. So hopefully you guys remember sort of like how compound interest works. So you have a certain amount of money or population or something, grows by a certain percentage, and then that new number grows by that same percentage, and you're just compounding the percentages on top of itself. And you can do that a certain number of times. So you can do it every year, every month, every day. I think your credit card does it every day. Or your bank account would compound your interest every year, right? So you get 1.1% every year, and then it keeps compounding on that. Continuous compounding means it's always compounding. Like there's, at any small fraction of time, it's putting on interest continuously the whole time. Like there's no, you can't count how many times it's compounding. So if you actually do that, you put $1 in the bank, and after a year, after continuous compounding, you'll end up with $2.71. So you'll almost triple your money if your bank decided to compound it continuously, which would be nice, but no one's going to do that. And that's a useful model for a lot of situations. I'm not going to give you any word problems at this point, because we will return to exponential models. In, I think, section 3.6, and we'll do word problems then. For now, I want you to know what the basic graphs look like. Remember your laws of exponents, and you're going to need to know some other things I'm going to tell you in 1.6. But that is 1.5. So we'll actually move on to 1.6 right now. Any questions on exponentials? I know I threw a lot at you guys, but it's because I kind of expect you to have seen it before. Probably never seen e to the x, but hopefully a to the x in general is something you've seen before. You've seen the graphs before and all that. And hopefully you know the laws of exponents. Is there no questions? Let's move on. 1.6 talks about the inverse of the exponential. This is going to talk about logarithmic functions. Called logarithms. Has anyone done logs before? Has anyone not done logs before? So here we do logarithms in pre-calc, but I'm not sure at other colleges they do that, or where you do that in high school. But yeah, we're going to review logarithms. Technically, you're supposed to know that as well. I just want to make sure you have the rules. So let's start with the definition of what a logarithm is. That's a logarithm in words. The logarithm of a number to a given base is the power to which the base must be raised to give the number. So when we're talking about logarithms, we're actually talking about powers. Exponents, in other words. Short for logarithms is log or logs. They provide another way exponential functions, or exponential equations. Which brings us to the notation. Okay, so the notation is the following. You write log, log. The base is a small number that goes down here, and the number is big thing that goes beside here, and that is equal to the power. So that's how we express logarithms. So it's the log of a number to a given base is the power that you have to raise this base to get that number. And that gives us another way to rewrite an exponential equation. And also leads us to the first law of logarithms. Law 1, which is basically the definition written in math symbols. Log to the base a of b equals c means if I take a raised to the c, I get the number b. So if I have this equation, I can write that. And if I have this equation, I can write that. They mean exactly the same thing. So I can give you an example here. For example, log to the base 2 of 8 is 3. Why? Because if I take 2 raised to the power 3, I get the number 8. Okay? So the log of this number to that base is the power that I have to raise that base to in order to get that number. So if I have to raise 2 to the power 3 to get 8, that's why the log to the base 2 of 8 is 3. So at this point, you might be wondering, why didn't we just stick with that? Why are the math teachers torturing us for no reason, giving us this whole new notation to write something that we know about already? Well, there is a use for it. Logarithms can greatly simplify complex equations. And today it might not mean much to students studying it, but these equations literally save lives. It was developed by, well, there were a couple of people who did it independently, but it's mostly noted that it was invented by this guy called Nader, and it was helping in nautical navigation. Way back in the day, people used to sail out on ships and never return because they couldn't navigate properly. And the calculations were very hard when you're sailing on a curved earth, and developing logarithms actually made them simplify their calculations fast enough so they could actually chart their destinations better, right? Because by applying a log to something, you can make distances smaller, and you can work with smaller numbers. And so these things literally saved lives back in the day. Here's another law that goes to what we're talking about. Logs turn powers into products. So instead of raising something to a power, you can now do a multiplication. If you have something raised to a power and you apply a log to it, you plug it into the log function, you can actually take that power and you can move it down in the front. It turns powers into products, right? And remember, we're thinking of logs as powers, so this is basically the exponential rule that says if I have something to a power raised to another power, I multiply the powers. So logs can turn an exponential into just a multiplication. So, example, if I have log to the base 2 of x cubed, I can rewrite that as just 3 times log to the base 2 of x. They're the same. So the log itself provides another way to rewrite an exponential, and it's useful because it can do things like get rid of exponentiation. I can, instead of raising something to a power, I can now do a multiplication, which would simplify your calculations a lot. Another thing that's useful is logs turn products into sums, because when I multiply two things of the same base, I add the powers. So if I have log to the base a of something times something else, turns out that I can just add them together. I can add the logs. So I go from a multiplication to an addition. So, example, log is 3 of 2x squared. That's the same as log to the base 3 of 2 plus log to the base 3 of x squared. I can actually split up a multiplication. That's the third law. before. Logs turn divisions into subtractions. When you divide things of the same base, you subtract the powers. So if I have something like log to the base 3 of 2 minus x squared over 3 radical x, I can write this as log to the base 3, 2 minus x squared minus log to the base 3 of 3 radical x. So if there's a division, I can write it as a subtraction and start breaking things down. In chapter 3, we're going to learn something called the Quotient Rule, and you're going to realize that logs will make that guy a lot easier as well in some situations. Law 5. It's called the change of base formula. This says log to the base a of b is equal to log to the base c of b divided by log to the base c of a, where c is a conveniently chosen base. What does convenient mean? Well, let me explain. Example. Let's say I ask you to find log to the base 4 of 8. So now remember that means I want to know what power I have to raise 4 to in order to get 8. Now at first, off the top of your head, you might not know what that is, right? Because you know 4 to the 1 is 4, 4 to the 2 is 16, you already passed the 8. So you know it's the number between 1 and 2. But what is the number? Is it 1.5, 1.25, 1.75? What is the actual number? You probably don't know off the top of your head, and you don't want to waste your time guessing. However, notice that 8 and 4, there is something convenient to express them as the base, right? What would be a convenient base with respect to 4 and 8? 2, right? I know what 4 is as base 2, and I know what 8 is as base 2. So in this case, my C could be the number 2, because it would be convenient because of the numbers that I have here. So what I could have done, I could have realized that this is actually going to be the same by the change of base formula. Log to the base 2 of 8 divided by log to the base 2 of 4. And what's log to the base 2 of 8? 3. Because I have to raise 2 to the power of 3 to get 8. What's log to the base 2 of 4? 2. Because I have to raise 2 to the power of 2 to get 4. So the number is 3 over 2. So it turns out that means that if I take 4 to the 3 over 2 power, I should get 8. Now what's 4 to the 3 over 2 by flower power? Square root of 4, and then you cube it. Square root of 4 is 2, and then you cube that. So you actually get 8, which is what you wanted. So the change of base formula can help you figure out what power you need when it's not that obvious at first glance. So that's actually a very powerful formula as well. And it's one of the formulas that we can use to transform things to base E, which I told you is very convenient for calculus. Here's a note. Memorize the first 5 laws. Know them as well as you know your own name, like the back of your hand. There are a few more laws though. some other laws. For this one, it is very highly recommended that you memorize them. But technically you don't. If you want to derive them from this, you can, but if you're not someone who likes deriving things, it's highly recommended that you just memorize these. It's not as hard as you might think. But there's no excuse for not memorizing the first 5. So this brings us to law 6. These are in no particular order, I guess. Log to the base a of 1. What is the log of 1? Based on our definitions, what do you think the answer would be? 0. Log of 1 is always 0 no matter what the base is, because if I take something to the 0 power, I will get 1. So that's something that you should just have memorized. You don't want to have to think about it all the time. That's wasting precious time. Here's another question for you. What is log of 0? If I take a to the power 1, I get 0. What would that be? A to the power a will give me 0. What if a is like 2 or something? 2 to what power will give me 0? What power of 2 gives me 0? 2 to the negative 1? What's 2 to the negative 1? Laws of exponents says that's a half. That's not 0. It's a trick question. It's undefined. There's nothing I could raise 2 to get 0. The base is 2. It's never going to be 0. It's actually undefined. Log of 0 does not exist. And we'll talk about the graphs of log soon, and you'll see why. So log of 0 actually doesn't exist. But log of 1 is always 0. No matter what the base is, you're going to put 0 as the answer. Law 8. There's only one punishment, and it is death. Anyone knows where that's from? You're all just kids. So young. Here's one. It says that if I have a log to the base a, and I put a to the x, the answer is x. Right, so that's saying something like that log to the base 2 of 2 to the x, the answer is just x. Or log to the base 3 of 3 to the x, the answer is just x. But it doesn't have to be x itself, it could be something else. So I could have log to the base 4 of 4 to the x squared plus 1, and the answer is x squared plus 1, right? Whatever is here is going to be the answer, right? If the base of the log and the base of the number that it's logging match up, then the power is what matters. What is log to the base 2 of 2 then? 1. Right? Because you can think of this as 2 to the 1 power, they match up. You can also realize that I take 2 to the 1 power to get 2, right, by the definition. So that's a law that you should know. If the base of your log and the number matches up, then the power is going to be the answer. Whatever the power is, doesn't matter how ugly it looks, it could be something a lot crazier than this. But that's what it's going to be. Law 9. It's kind of the opposite. That says if I have the base a, and in the power, I put log to the base a of x, that's actually x. So if I have 2 raised to log to the base 2 of x, that's just x. Or if I have 3, and I have log to the base 3 of x cubed plus 7, that would be x cubed plus 7. Right? So if the base and the log match up, you can think of them kind of canceling each other, which I'm going to talk about later on. Parenthetical statement. Laws 8 and 9 show that, or illustrate that, y equals a to the x and y equals log to the base a of x are, what's the name for these two guys? Inverse functions. So hopefully you remember, an inverse of a function is just a function that does the opposite of what the function did. Right? So the function would do something and the inverse would undo it, put it back. Right? So inverse functions have this property. F of x, g of x are inverses if I plug f into g, g into f, I get x, and if I plug f into g, I also get x. This says g would do something to x, but f is just going to put it back. It's going to give you back the original input. Same thing, f might take x somewhere else, but g is going to give you back the original input. So if you plug one function into the other one, it just gives you the original x value. So that's what we did here. If I plug the exponential into a log, it gives me the original value. And if I plug a log into an exponential, it gives me the original value. Right? They undo each other. They can actually cancel each other. So once there's a log beside an exponential, you can just forget this. This cancels out, and you're left with that. And if you have an exponential beside a log, they cancel out, and you're just left with that. You can think of it that way as well. Because they're actually inverse functions. Last law, law 10, like the 10 Commandments. It's more of a notational thing. Now, I mentioned to you that e, the exponential with e to the x, is a very important function. So when I have log to the base e, we consider this so important that we actually give it a different notation. We write ln. Now this is called the natural log. It's the log that is natural to do calculus with. E to the x is called a natural exponential function. E is called a natural number. So this is called the natural logarithm. Right? So whenever you see this, it's just a log, but the base is e, right? But they didn't write it. If you just see log of x, it means log to the base 10. Right? So if they don't write a number, the base is considered 10. Right? So ln x means log to the base e. And any other base, they'll write it down. They'll tell you. Right? So any other base, other bases will be expressed explicitly. So 10 is important. We have 10 fingers, and raising things to the power of 10 is easy. E is important, so we denote those. So these two guys are special in the notation. So if they don't write a number here, you must assume that the base is 10. And if they write ln, assume that the base is e. So whenever you see ln, just remember, it's just a log like any other log. The difference is the base is e, which means all the previous laws apply to ln. And so it's the laws that you're going to need to know. Consequences of law 10. So this means, for example, ln of x to the n just n ln x, it'll work just like a normal log function. Or if I have ln of something times something else, it's ln of this plus ln of that. If I have ln of something over something, I can just subtract the ln's. And if I have something like ln of x equals y, it means e to the y equals x. Because the base here is e, it means if I take e raised to that power, I will get this number. Right? But they don't write the base number. And also, just as you can cancel log to the base a with a to the x and vice versa, you can cancel e to the x ln x and vice versa. Probably how you'd want to remember this is to get rid of a log, use an exponential. And to get rid of an exponential, use a log. So that's how you're going to want to think about it. What do I actually mean? Well, if I have y equals ln x, and let's say I want to solve for x, right? In other words, I want to get rid of that ln. The way to get rid of that ln, right? It's just talking about like solving equations. Like if you had y equals 2x and you wanted to solve for x, you know, you have to divide by 2. There's an operation that will get rid of that 2, right? To get rid of something like a log, you use an exponential, right? So what you do is if you have y equals ln x, you want to solve for x, get rid of that log, you use an exponential. So you plug each part into an exponential function. So you say you e both sides, is what we might say. And what happens is the e and the ln, you think of it as canceling. So that will give you x equals e to the y, which you could get from the definition, but you can also think of it as just canceling one with the other. Or if I had y equals e to the x, and I want to solve for the x that's right here, because that's an exponential, I can get rid of the exponential by doing a log. So I can log both sides, right? Plug both sides into a log. What's going to happen on this side? ln and e will cancel, and that will give you the x. And I'll get ln of y on this side. That's going to be the solution. Right? So to get rid of a log, use an exponential. To get rid of an exponential, use a log. And that's going to be very important in solving equations. That was a mouthful. Any questions? Or I don't even know if you have questions. I don't even know what's going on. What do I ask? I don't even know what a question would be right now. Okay, let me give you some things to do, and then you tell me if you have questions. Some examples. Evaluate the following. So you'll know if you have questions by doing this. A. E to the 5 ln 2. Meaning, rewrite it as a number. Kind of simplify it. 2 to the log base 2 to the 5. I'll try and do this. Right, so start doing 2 to the log 2 of 2 to the 5. Ln e. Ln 1. E to the ln of x. Then e to the x. C, D, E, F. G log to the base 2 of x minus log to the base 2 of x squared plus log to the base 2 of x to the 4th. H e to the ln of x squared minus 5 ln y.
That's an S for B.
Come again?
For B, that's 2 to the S. Or 5.
No, 5. That's a 5. I have one more example, but no space. Okay, so let's go through this one by one. It would be good if you write down what you think the answer is, or try to work it out without just watching me. Okay, so some brave soul, tell me what this is. No?
5 ln.
That's the answer?
2 to the 5th. And then 2 to the 5th.
How do you get ln 2 to the 5th?
Hold on. So what I did was I put a ln next to the e. I canceled. Then I got 5 ln and then 2. So as the 5 is in front of ln, it becomes an exponent.
Okay. And
When
so
you have a
what's
number
your...
in front, it becomes an exponent.
You can write it as an exponent, yeah.
Yeah.
So remember what I just mentioned about an exponential and a log canceling each other. One important thing to note is that the e and the ln have to be right beside each other. There can be nothing in between, right? Right. The coefficient of this has to be 1. Say in my last class, oh, nothing should be in the ln. There's the 1 in front of that. Okay. So there's a 1 in front of this ln, right? There has to be a 1 in front of the ln. If it's anything else, you can't apply this rule. You can't cancel it. The fact that there's a 5 here in between the ln and the e makes the cancellation rule, it doesn't work. So the first goal would be to get rid of that 5, which, as you said, there's a law that says if there's something multiplying, I can actually make it a power, right? So that would be the first step. So don't just go, oh, e and ln, and start canceling all over the place, because if it's not in the right form to cancel, it won't work, right? So the first thing you're going to do is to write that, right? Which was log 2 or something. Right? And so now the e and the ln is right beside each other. They cancel. And so now the answer is actually 2 to the 5th power, right? Which I heard someone say, but I didn't want to point it out. Which is 32. So that's just a fancy way of writing 32. Just confuse me. So you can just confuse everyone. What's the answer? E to the 5 ln 2. Just to mess with me. Just to show off. Yeah, I'm in calculus. Okay. What about this one? How do you get that? What cancels where? Yeah, so the 2 base 2 and the log 2, they're the same base. So I can cancel this one. I can even cancel these two. You get the same thing. But this 2 would cancel that. And so I just get left over with what's in the log. So it's again another fancy way of writing 32. What's the answer? 2 to the log base 2 of 2 to the 5th. Okay. What about ln of e? It's 1. Right? Because remember with ln, the base is e. What power do you have to raise e to get e? 1. Right? It's also log 8. I think. What's ln of 1? 0. The log of 1 is always 0. Doesn't matter what the base is. It's also true if the base is e. E to the ln x. Just x. E and ln cancel. ln of e to the x. It's x. ln of e cancel. What's that one? Okay, so you go look at these first 2 first. You see, oh, you have log of something minus log of something else. Now we have a rule for when you subtract in logs, it becomes a division. So the first 2 gives us x divided by x squared. Because I know a log of a division is just a subtraction. Right? This guy is just here hanging out for now. And now I have log plus a log. So what can I do now? I can multiply them. I can put it into one log and multiply these. X over x squared times x to the 4th. So what am I left with? Well, x squared goes into this 2 times, so I have x times x squared. That's just x to the 3rd. Or you can bring that 3 down. It won't really matter. So these 3 terms I could simplify to that. What about this one?
Cancel the ln and the e to the ln x squared minus y to the 5th. Over.
How would you get that?
You have the same base.
Why couldn't I cancel this and just say that's the answer?
Because you have another minus.
Because there's a whole other thing, right? So it's like, there's a rule that says if I have e to the ln of something, I can cancel it. But what about if I add or subtract something else? The rule doesn't apply anymore, right? It doesn't look like that. So the fact that I subtracted something else in the power means that I have to rewrite things first. So now's where we remember laws of exponents, right? If there's a subtraction in the power, what does that mean? As someone says, it means a division. So this is actually e to the ln of x squared divided by e to the minus 5 ln y. So that's the first step, to realize that a subtraction of power actually means a division is happening. Right? Now on the top, my e and my ln is right beside each other. It's getting really dramatic. Okay, so e and ln will cancel each other here, and so my numerator is just x squared. What about the denominator? Right, so here I would move that 5 up, y to the 5th. So I have e to the ln of y to the 5th, just y to the 5th. So that's actually the answer here. Any questions on any of these? It's going to be very important that you know these, not just for this class, but also for 209. Like the first 3 or 4 chapters in 209, you're going to be doing things with ln's and e's like all over the place.
I have a question.
Yes?
What happened to the negative?
Oh, because the rule that says if I have a negative in the power, it's just 1 over the thing to the positive power. Like I get rid of the sign once I put it down. Here's another example, which it might seem counterintuitive to you at first, like why would you want to do that? But trust me, there's going to be times where you're going to want to do this. I want you to expand something. So before what I did was, here was something expanded and we actually contracted it into one log. Now I'm going to want you to do the opposite. I'm going to give you one log and I want you to expand it as much as you can. So all of that is that's one big log, expand it. And that's going to be our last example. We're not done with 1.6, but we'll stop after this because we only have a few minutes left. Okay, let's begin. What do we do?
Subtract.
Subtract what?
ln square root of x squared minus 1 minus ln x times x plus 2 squared.
Right. So this guy sort of looked at it and it looked like ln of a over b, right? Or x over y, right? There's just one thing divided by another thing. It looks complicated, but you really want to look at the form, right? There's a division happening, right? And I have a law for that that says I can just take ln of the top minus ln of the bottom, which is what we did in the first step. Now what?
I started with the second one.
So you didn't do anything with this?
I was confused.
Can we
about
do
that
anything?
one.
Right, as an exponent, because we know how to change things with exponents. So what would that be?
X squared minus 1 to
The
the
1/2 power, right? So let's leave that for a moment. What do we do here?
Then you change it to addition. So ln plus x plus 2 ln.
Stop skipping steps on me. No, it's smart as here. Okay, so you start with there. Right, is that okay so far?
Yeah.
Nope. What's wrong?
Parentheses.
Parentheses.
Oh.
Be careful. This negative sign has to be distributed. Right? Okay. So let's take another step. Can we do anything to this guy?
Yeah.
What?
Move the 1/2 to the front.
1/2 can come down, that's by a law. So this I can write as 1/2 ln of x squared minus 1 minus ln x minus, because now I'm distributing. And this 2 can come down by that law, 2 ln of x plus 2. Can we do anything else? What?
No.
What else can be done? Divide what? Where? No, well, if we start dividing, we're going to start to get this guy back. So we don't want to do that. I want to spread things out. Can we do anything else?
To get like the fraction or the
We can't multiply by 2.
Just factor x squared.
No. We're simplifying the expression, not solving and creating. So we can't like multiply both sides by a random number. What is x squared minus 1? It's a difference of squares, so how can I write that? Can I do anything here? it's a multiplication, so I can turn it into addition. So it's ln x plus 1 plus ln of x minus 1, and parentheses, so that the half gets distributed. So I could do something like 1/2 ln of x plus 1 plus 1/2 ln x minus 1 minus ln of x minus 2 ln of x plus 2. And this one I can split up, right? 2 ln x plus ln 2, right? No. That's not a rule. There's no rule for expanding a plus in an ln, right? Remember, to add ln's, it comes from multiplication. So I did that. I know it's going to be tempting to do that. You're going to say, oh, I can just distribute it. You cannot distribute ln's, right? That's one thing you need to know. You can't just distribute, oh, ln of x and ln of 1. It doesn't work. So that would be pretty much expanded as much as we could. And when we get to chapter 3, you'll see why would we want to do that. Why would we want to go from this thing that's all nice and compact to that thing spread out all over the place. You'll see that there are rules that we're going to want to apply to these functions where in this case it's going to be really complicated to apply the rule, but in this case it's going to be like really easy to apply. For now we'll stop there. We'll talk more about logs later on. We'll do some more equations, and I'll also talk about the graph of logs. Yes. Quiz on Monday.
On the stuff from Monday or on this?
On the stuff that I did on Monday and today.
Oh.
Yeah. So we'll stop there. See you guys on Monday.